Welcome back. This is Mr. Hassan's Maths channel, and in this video I'm doing 11 part 2 from the October-November 2019 International A-Level Cambridge 9709 paper. This is the variant 3, paper 1-3, and this question is also question number 6 from my end of topic worksheet on integration from P1 Cambridge. And here we have a question all about volumes of revolution. So it says, find, showing all necessary working, the volume of revolution obtained when the shaded area is rotated 360 degrees about the x-axis. So part 1 we already did, and it's on a separate video. And in that question we had to find the equation of this normal to the curve at this point, which we found was the equation that was y equals a half x plus 2. And now we have to find the volume of the region formed when this shaded region is revolved around or rotated 360 degrees around the x-axis. Okay, so it's going to be kind of coming out of the page and then going back into the page. Going to make like a three-dimensional shape. Now, if you can't really picture that, I'm going to show you a little animation to help you understand exactly what that means. Okay, so this area, just imagine you have an area like this, and you want to rotate this area about the x-axis between the points A and B. So let's say we call this A and this B. Okay, between those 2 points. So when you rotate this area about the x-axis, okay, this is what's gonna be formed. Okay, so it's like it's gonna come out of the page and go around, forming like a three-dimensional shape, as you can see. Some sort of kind of a bell type of shape we can see here. Okay, so that's what it means by the volume of revolution, or the solid of revolution. Okay, it's when you take the shaded area and it revolves, it kind of wraps around the x-axis, one revolution, and you get this volume. So we have to find the volume of this shape which has been formed when this is revolved around the x-axis. Now, in order to do that, what we can do is we can consider just like a small slice of this shape. Okay, we can consider, for example, a small slice of this area, and we can consider it so small that it basically makes a rectangle. It's like a rectangular shape. And when you rotate that rectangular shape around the x-axis, what you're left with is like a very thin cylinder. Okay, very, very thin cylinder. So if you rotate this around the x-axis, you find that you get this very, very thin cylinder. Okay, and this cylinder is such that its radius is like the y value of this point here. That would be its radius, and its height would be like this thickness of the cylinder, which is a small amount in x. So what we do is we call this small amount in x, we call it dx, a small little tiny amount of x. Okay, and then what we can notice after that is this cylinder, as I said. Okay, it's a very thin cylinder of radius, and we're going to call it y here, and its height is a very tiny part of the x-axis, which we call x. dx, sorry, small part of the x-axis called dx. So the volume of a cylinder, as we know, if we look at a cylinder, the volume of a cylinder is the area of the base, which is like a circle, pi r squared, times how high it is, h. Pi r squared h, that's the volume of a cylinder. So in this case, we have our cylinder having a radius of r, the radius of y, sorry, that would be the radius, and the height of the cylinder would be this small little x. It's like a cylinder on its side almost. Okay, so the volume is pi r squared h. So this will be pi r squared, or pi y squared times dx. You can say, what we can say here is this is a small little slice of the volume, okay, of this whole thing is pi times r squared, pi times y squared times dx. Okay, dx is a small thickness. So if we add together all of the volumes of every cylinder from A to B, we add them all together, we'll get the sum of all of the pi y squared dx's from the beginning to the end. So this formula here represents the volume of this cylinder, okay, and all the other cylinders between A and B added together, considering them to really, really small. Okay, so that's basically some sort of basic crude explanation of what's going on here in this integration. So this formula, we should know it. It's not going to be given to us. We have to be able to quote it. All right, so some people memorize it like this: pi y squared dx. I like to write the pi outside the integral sign generally, although sometimes you have to be very careful in case you forget the pi. Don't forget the pi. In this, a lot of people forget about the pi. So that's basically how we can understand the formula for the volume of revolution of a shaded area when it revolves around the x-axis. Okay, so now we've understood hopefully why this formula, the volume of revolution, is equal to pi times y squared dx between the limits of a and b, will tell us the volume of revolution of a solid, okay, when this area is rotated around the x-axis. Okay, so hopefully that will give you understanding of why that gives us the volume of revolution. Now I'm going to apply it to this particular question here, and what we're going to do first is we're going to see here very clearly there's a distinction between this first section here, between 1 and 2, and between 2 and 3. First section here has a different equation completely. Okay, that's a straight line, which we found the equation of in part 1. And so that's between 1 and 2, you have this straight line, and between 2 and 3, you have this curve. So we need to do this in two separate sections. I'll call this section 1 and section 2. Find the volume of section 1 when it's rotated around the x-axis, and then add to that the volume of section 2 when it's rotated around the x-axis. So I'm going to do two separate calculations for that. So the volume of section 1 is going to be given by pi times the integral between 1 and 2, those are the limits there, of y squared. Y is the equation here for this, in this case, half x plus 2. I've got to square that, and then I have to integrate with respect to x. Okay, so a few things here. Don't forget the pi. It's very easy to forget about the pi. That's why a lot of people like to write that inside. I prefer to keep it outside, but just keep it in your head. Don't forget the pi. Okay, now to integrate this, I could continue and simplify this by expanding and write them as separate terms, because it's only squared. It's not a big deal to do that. But because we're able to reverse the chain rule here, I think it's better to do that myself personally. So I'm going to reverse the chain rule. You can check to see if something is able to be integrated by reversing the chain rule by finding the derivative of what's inside the bracket here. So the derivative of a half x plus 2 is a half, and check what's multiplying this bracket. Now there's nothing, well, basically it looks like nothing multiplying the bracket, but in fact there's a 1 multiplying the bracket. It's 1 times this. So there's a 1 here that's multiplying the bracket. That's a constant. And what the derivative you found is also a constant. So you can now reverse the chain rule. Like if there was an x out here, you wouldn't be able to do that. Okay, because out here would be something which is not of the form, it's not like a multiple, or it's not a constant times the derivative of what's inside the function. So we can do that here. So to do that, reversing the chain rule, pretty simple. Once you've started integrating, don't write the integral sign anymore. Okay, just write your square bracket, and don't put the limits on this side, you put them on that side once you've integrated. So to integrate this, I'm going to take this expression here, a half x plus 2. I'm going to add 1 to the power. Then I'm going to divide by the new power. And also I'll divide by the derivative of what's inside the function, which is a half. And my limits, as I said, we're going to write on this side now, 2 and 1. Let me write this now a bit simpler. I know that 3 times a half is 3 over 2. When I divide something by 3 over 2, it's like multiplying by 2/3. So I'll have 2 over 3. And don't forget the pi. Don't forget the pi. The brackets, and inside here you have a half x plus 2. And you have the limits from 2 to 1. So now we're going to substitute in those limits and find our volume. So volume 1, therefore, is going to be 2/3 of pi times, I'll put 2 in here first. So half times 2 is 1. 1 times 2 is 3. So that's 3. Okay. And that's cubed, by the way. I forgot the cube. Sorry. That's cubed. Don't make silly mistakes like that. So that's 3 cubed minus, and 2 times 1 times a half is a half. A half plus 1, a half plus 2, sorry, is 2.5, which is 5 over 2. So that's 5 over 2 cubed. Okay, so that gives me 2/3 pi times, that's going to be 27 minus 125 over 8. Okay, so that should give us our answer. So we have 27 minus 125 over 8. That gives me 91 over 8. If I multiply that by 2/3, that gives me 91 over 12 pi. So we can say the volume of 1 is 91 over 12 pi units cubed. Okay, don't forget the pi. Don't forget the pi. So that's the volume of this when you revolve it 360 degrees around the x-axis. Now we've got to do the same thing for that second volume. So we have the volume of section 2 is going to be pi times y squared. Now in this case, y is it's all of this, x minus 1 to the power of -2 plus 2. All of that is going to be squared, and then you integrate with respect to x, and this time our limits are between 2 and 3. So when I find the value of this, that should give me the second part of the volume. Added to that, I'll get my answer. Okay, so here we can do this. We can get this ready for integration. In fact, yes, here we cannot reverse the chain rule, of course, because if you differentiate what's inside here, there's no way you get anything which is a derivative of that on the outside. So here, because it's only raised to the power of 2, we can actually expand this bracket. Think of this as one term. So when you expand a bracket, so now I haven't started integrating, so I'm going to keep writing the integral sign until I started integrating. I'm preparing it for integration. So what I'm going to do here is I'm going to, remember, if you have a plus b all squared, and you want to expand that, you can square the first term, and you can multiply these together and double them, and then you can square the last term. So I'll do the same thing. I'll square the first term. That's going to give me x minus 1 to the power of -4. That's what happens when you square that, right? Raise it to the power of 2. Then I'll have 2 times these two multiplied. So I'm going to have plus 2 times 2, which is 4, times this bracket as it is. And then I'm going to square the last term. So square of 2 is 4. So that is my that is preparing this to be integrated. Okay, so I've prepared this for integration, okay, by raising everything, raising it to the power of 2, squaring that bracket. Now I can integrate. So, and when I start integrating, don't forget the pi, as I'm going to keep mentioning. Now we're going to put a square bracket because I'm actually going to integrate now. So the first term, I've got x minus 1 to the power of negative. I have to add 1 to the power, so it becomes -3, divided by the new power, which is -3, multiplied by the differential what's inside the function, which is just 1. That's fine. And then I'm going to have plus, and again, I'm going to take the 4x to the power of -1, raise the power by 1, that becomes a -1, divided by -1, again, multiplied by the differential what's inside, which is 1, and 4 just becomes 4x. Okay, so now that's, the limits here are 2 and 3. So now let's just simplify this a little bit before we substitute. So I'll do it down here so I get more space. So pi times, don't forget the pi. Now I've got here, this is going to be a negative term, and this is to the power of -3. So what, to make it easy for substitution, I'm going to write that in the new denominator. So for example, I know that a to the power of -n is the same as 1 over a to the power of n. So I can rewrite this as 1 over, and I've got 3 times x minus 1 cubed. That's how that will be written in a more friendly way for substituting values in. And here you got a negative term, because this is a positive, that will be a negative term, so I'll put minus. And again, here I'm going to have 4 on top, over, and then this part can go in the denominator as x minus 1 to the power of 1. So just x minus 1 plus 4x. And then I have my limits of 3 and 2. Now, hopefully, if I do everything right, if I put these limits in, it should give me my answer. So just do this carefully. So I have minus 1 over 3 times. That's going to be 3 minus 1, which is 2 cubed. Minus 4 over 3 minus 1, which is 2. Plus 4 times 3, which is 12. We'll work that in a minute. Minus. And then I'm going to put a bracket to protect these from the minus sign. I'll put 2 in here. So I have minus 1 over 3 times 2 minus 1 cubed. So that's 1 cubed, which is going to be 1 there. And then minus 4 over 2 minus 1, which is 1. Plus 4 times 2. Okay, let's see what that gives us. That's going to be pi times, that's going to be minus 1 over, that's 3 times 8, which is 24. Minus 2 plus 12 minus, that's minus 1 over 3. minus 4 plus 8. Okay, so we're almost there. So let's work out what this is. I can just stick this in my calculator now, and we should get the answer. So I'm going to have 12 minus 2, which is 10. So let's just write minus 1 over 24, minus 2, plus 12, minus, brackets, you have minus a third, and you have minus 4 and plus 8. Close that bracket. That gives you 151 over 24. That's 151 over 24. Don't forget the pi. That's units squared, cubed. I put cubed there as well? Cubed, yes. So now we got, that's volume 2 now. That's the volume of part 2. So we found here is the volume of section 2. All right, so now we can say that the total volume we need is volume 1 plus volume 2. And volume 1, as we saw before, was 91 over 12 pi. 91 over 12 pi plus volume 2, which is 151 over 24 pi. So what does that give us? We have that plus 91 over 12. That gives us 111 over 8. That's 111 over 8 pi units cubed. Okay, you can leave your answer like that. That's fine. Let's just check actually. What did they say in the question? Okay, whoops. Okay, so let's have a look. It says here. Okay, it didn't tell you how to round your answer, so you can leave your answer like that. That's perfectly fine. If you wanted to then multiply this by pi and then write it as a decimal, you could. If you want to write as 43.6, okay, 43.6 units cubed. Okay, I personally would leave my answer like that. I think that's a neat way of writing it. But there we have the final answer for this question. It's a bit of more of an involved question about volumes of rotations. 8 marks here, because you had to basically do it twice, one to this straight line and one to this curve. We could have also used the volume of what's called a truncated cone in order for us to find the volume of this if you rotated it around, because you have the radius of the top part, the radius of the bottom part, and you have this, height of the but that's going to be complicated. You have to recall the volume of a truncated cone or use similarity to find it, but that's not necessary. It's easier, I think, here just to use the volume, find the volume by doing the integration. So anyway, that concludes this question. I hope that was clear. And, as I said, part 1 of this question is in a separate video, which is going to be linked at the end of this video. So at the end of the video now, you'll probably see a link here taking you to the playlist on which you'll find the other questions from this paper, including part 1. So if you want to find part 1, you can click on that. The playlist, you'll find it there. In this place here, you'll find a link to the other questions that I have answered from this integration worksheet number 3 for my P1 collection of Cambridge. Other questions in general from integration of P1 of Cambridge you can find in this link over here. And you can subscribe to my channel by clicking on the link shown in this section here. And if you would like to find how to, access my other material specific to Edexcel or my IGCSE material, then please, click on the card that's been showing during this video, which takes you to a video where I explain exactly how to navigate my channel. In fact, I'll put that video over here instead of the subscribe. I'll put it over here. Click on that video. It will take you to a video explaining how to access my other material easily. Thank you for watching and see you soon.